We're going to take a look at Chapter 16, Exam 8. This is the next to the last chapter exam. We'll have one more chapter exam after this, and then we'll review for the final. So this exam is going to be on Thursday, this Thursday. Show up in person. I'll be here with a paper test. If you don't, I'll be zoomed in case you have any problems you need to discuss, and check in with me at that time. So let's kick it off with, let's see. Oops. I have to turn it on. There we go. Number 3, where we're going to start this one. Right. Which of the following is the strongest conjugate acid? Okay. I think the best approach to this problem is to look at the group that's attached to the hydrogen. The strongest acid is going to be the one that draws the most electron density to itself. And of the ones that are given, and then we have all the same. I'm pretty sure that they're not all the same. First of all, is that even valid? That's not even a valid compound, right? What should it be? It should be that if we're going to look at it at all. So that means D cannot possibly be it. That means since this one is not possibly it, they can't all be the same. So now we're looking at A, B, and C. HCN and HF. At this point, we're looking at the electronegativity, so to speak, of the groups that are attached to hydrogen. We know that fluorine is the most electronegative element in the periodic table. So this would be a good candidate for the strongest acid. Hydrocyanic acid is a weak acid. Well, this is a weak acid too, but it's not as weak as that one. And this is hypochlorous acid. This was hydrocyanic. And this one is hydrofluoric. If you don't have any other information, say to tell you what is the K value, we don't know. We're not given the Kas for each of these acids that would tell us quantitatively what their dissociation looks like. So we have to assume that not only do we need to know the strongest electronegativity, but what's the size of this part of the molecule, right? We know that carbon and nitrogen are electronegative, but they're not as electronegative as fluorine. So that lets them out. Chlorine and oxygen together are likely candidates for a competitor to fluorine. The problem is oxygen and chlorine together make a huge polyatomic ion. And if you spread the electron density over a larger space, it has less concentrated power, so to speak, to draw electrons away from the hydrogen, because that's what you want to do. If you draw electrons away from the hydrogen, it makes it easier to leave the molecule. So fluorine being a very small atom, and the hypochlorite polyatomic ion is much, much bigger, even if they were the same electronegativities, then this one would win because it is more dense in electric charge. Okay, that's the best I can do with this one. All right, so that's why the answer is C. About number 4, calculate the hydrogen ion concentration at equilibrium, notice the square brackets, in a solution that has a pH of 8.82. And the question is, what is this? First of all, do we have enough information? Well, they're related, pH and hydrogen ion concentration. Oh yeah, they're related. pH is equal to the negative log of that value. Okay, so I think we have enough information. If we put the pH here, negative log, now we have an equation in one unknown, so we can solve it. We just have to know how to deal with logarithms. Okay, so by definition, remember logarithm, the common log has a base 10. So by definition, that value is the power of 10 for this value. Except we can't have a negative value here. So what we have to do is move it over here. I'm going the long way just to show you every minute step. That means that this power, this 10 to that power is equal to that. That's known as the anti-log of this value. And this is the way it would look on your calculator. You would have 10 to the x, and the x would be the negative of that pH. So all I have to do now is punch in 8.82 negative sign and then go to my 10 to the x. And since we have 2 decimal places, that means we need 2 significant figures in the answer. So this one would be 1.5 times 10 to the minus 9 molar. There it is. Okay? Let's see if I can page. Yep. Number 5. A solution is prepared by dissolving 111.9 grams of HCl gas. Dissolving that in enough water to make 160 liters of solution. So the final volume is 160.0 liters of solution. What's the pH? So remember, what we need to determine pH is the hydrogen ion concentration. Well, what is the hydrogen ion concentration? HCl, when you dissolve it in water, completely dissociates. It's a strong acid. So it's going to make Well, first of all, we have grams, right? You can't use grams in calculating the molarity of the acid. That's what we need. So we have to convert this to moles of HCl first. Right? Conversion factor time. So that means molar mass, correct? So what's the molar mass of HCl? Well, there's hydrogen. And look it up in your periodic table. There's chlorine. This is 36.46 there. So we divide this into that, and we find out the number of moles of hydrogen chloride. And I get 3.0691 mole of HCl that we put into solution. Now, how many moles of hydrogen ions is that? Exactly the same, because that's a strong acid. So now we can calculate the concentration of hydrogen ions is equal to 3.0691 divided by volume. And I get 1.918. 1.918 times 10 to the minus 2 molar. That's the hydrogen ion concentration. So if we take the negative log of that concentration, we should get pH. Change the sign, and then take a log of it. Oops, excuse me. My mistake. 1.918 exponent. Take the log first. Sorry. And then change the sign. And let's see. 4 significant figures. Actually, I got 5 here, so I need to pare it down to 4. And the number of decimal places in our answer should be 4. 1.7172. pH. Okay. All right. So the best answer here is 1.72. But since none of these is a possibility, and if you're strictly speaking, sticking to the, mine's gone blank, significant figures, then you should have as many decimal places here as you do significant figures in, and that should be 4. So this is truly the answer. Best answer is 1.72, but you could make an argument that E would be the correct answer because it's not strictly speaking that value. So you have it open there for an argument if you want to make one. Okay, that was 5. How about 6? Yep, 6. A solution has hydroxyl ion concentration equal to 5 times 10 to the minus 4 molar. What's the pH of that solution? You have 2 choices. You can calculate the hydrogen ion concentration using the Ka value. Right? You can say 1 times 10 to the minus 14 equals that times that. Plug this in here and solve for that one, and then do your pH. Or you can do POH. Negative log of 5 times 10 to the minus 4. Once you know POH, then pH is equal to pKa, actually pKw, or water, divided by pH, POH. I like this one better. So let's see what this value is. 5 times 10 to the minus 4. Let's see, 3.30. 3.30 is the POH. So that means pH is equal to 14, which is pKw, divided by 3.30. And let's see. What did I do wrong? I did something wrong. POH. Let me try that again. 5 exponents there. Log. Negative. That's correct. Oh, I know exactly what I did wrong. That was a dumb mistake. 14 minus 3.30. Because we're in logs now. Logs convert multiply, divide into add, subtract. So 14 and 3.3, that's 10.7. So pH equals 10.7. There it is. All righty. 7. Let's do. Let's scroll this up a little bit. Oops, too far. There we go. All right, number 7. I think this will start to give out on. Got a spare one. Number 7. As water is heated, its hydrogen ion concentration increases. So if we increase the temperature, then the hydrogen ion concentration also increases. Okay? That makes sense. If you add kinetic energy to each of those water molecules, when they hit one another, they tend to be more reactive and transfer protons. So that will increase this one. All right, well, what happens also? Think of it this way. In water, you've got these two guys coming together, and they're making what? Hydrogen ions and hydroxyl ions. So if this one increases, what's going to happen to that? That one increases by the same amount. Right? So the ratio, they're always equal. So let's look at our choices. Water is still neutral. Yeah, as long as this is equal to that in concentration, water is neutral. So even if you increase the temperature, the water is still neutral. It just has a higher concentration of hydrogen and hydroxyls. They go up together. So A is true. B, no. You don't get a difference here. You don't get a difference there. Hydroxyl also increases. That is true. So that means A and D are both true. That's why the answer is E. Okay, number 8. Identify the Bronsted acid and base in the following equation. A equals acid, B equals base. All right, let's see what we got. We got HSO3 minus. HSO3 minus, which is what? That's the hydrogen sulfide polyatomic ion. The cyanide polyatomic ion. And hydrocyanic acid plus, should have started further to the left, SO3, 2 minus, the sulfite ion. Okay, let's identify the acid and the base. First, on this side. This one should be obvious. Which one's the acid? It's the only one that has a hydrogen that can be transferred. This one. So that's the acid. This is the receiver. That's the base. Now we know that for the base, there's a conjugate acid. And for the acid, there's a conjugate base. So it should be AB, AB. All right. That was pretty easy. All right, let's scroll. Yeah, number 9. Which of the following is a conjugate acid-base pair? Right? Remember what I said about acid-base pairs. If you have an acid with more than one hydrogen ion, and when it dissociates, it does so 1 proton at a time. So it would look like that. Now that's not exactly what we've got up here, but that's just an overall requirement for an acid-base pair. So this would be the acid, this would be the base. Okay, so let's look at what our choices. How about HPO4 2 minus and PO4 3 minus? That looks like a good candidate. We still have the PO4 part of the molecule over here, and this part is missing only 1 hydrogen. So this would be the acid, this would be the base. So A is a good candidate. Well, we found our answer actually. If we looked at the others, we'd see this one has gained a proton. Besides, that's not a valid molecule. Right? You know from polyatomic ion here, you can only have 1 proton. Right? If you put 2 protons in there, you'd have to have a positive charge for that group. Like that. Right? So that can't be it. This one's impossible too. NH4 plus, and if you have a hydrogen added to it, it should go negative, right? Not positive. And what's more, that's not a valid molecule either. How about this one? H2F. Fluorine ion is 1 minus. So you can only have 1 positive hydrogen attached to it at a time. So this would be the acid. but the base would be F minus. And this one, if you has lost 2 protons. So if it lost 2 protons, there should be Cn2 minus, which is not valid either. So we found our right answer. A is the correct answer for the conjugate acid-base pair. How about number 10? Choose the case that is not a Bronsted conjugate acid-base pair. So we got to choose the one that doesn't work. All right. How about this one? HCN and Cn minus. Right. That works. That's an acid. That's the base. Okay, so A works. How about B? CH3, NH3, that's supposed to be a plus. It's hard to see it. Plus. And then it says that this one should be NH2. So we need an H plus over here. Right? This would be the acid, this would be the base. That's true, it only lost 1 proton. Right? So B's good. A's good, B's good. How about C? HCOH, CO2H. Right? That's formic acid. And then it's saying that this one is the conjugate base. What's wrong with this picture? It didn't lose a hydrogen, it lost an oxygen, right? So we can't do that, right? You got 2 here and only 1 there. So I think we found our answer. Should be C. How about this one? H3BO3, which is boric acid, and H2BO3. That should be a minus. Yeah, that should have a minus here because it lost 1 proton. All right, so that's a problem. We'll make a note of that. Let's see. Well, in the printed copy, it's there, but it's missing here. There's a typographical error. But given that correction, that one's correct. That one's true also. And then the last one, HClO2. And it says ClO2 minus. Yep. Charges balanced. There's the part of the molecule, both sides. We've got a valid acid-base pair here also. So the best answer to this one is C. That's definitely not an acid-base pair. All right. Oh, I'm going to have to scroll this one. Let's see here. Here we go. 11. Calculate the hydrogen ion concentration in a solution that has a pH of 9.16. We've actually done this operation in the previous problem, but we go back to the original formula. Right? What do we know? We know that the pH is 9.16. And so all we have to do is take that negative sign, put it over here, and then we make this the power of 10. So 9.16, change the sign, and then do the power of 10. And I get an unexpected answer. Let me try that again. 9.16. Big. Oh, okay. Let's see, we have 2 decimal points, so we get 2 significant figures in our answer. 6.9 times 10 to the minus 10, I believe. Yep, molar. There it is, right there. All right, page. Skip 12 and 15. Calculate the pH of an acid solution containing 0.044 molar HNO3. 0.044 molar HNO3. That's a pretty low concentration for a strong acid. So the potential here is for this concentration to be so low that it's less than the pH of the water, which would be 7. So let's see. What is actually the 0.044 molar HNO3? So let's just do the calculation. Minus negative log of 0.044 and just see what we get. Okay, let's see. 2 significant figures, that means 2 decimals in our answer. 1.36. Okay, so that is low enough. It will change the pH of the water significantly. So 1.36 is the valid answer. (16) What's the pH of 4.9 molar solution of HClO4? Let's see. Hydrogen ion concentration. HClO4 is perchloric acid. It is very strong. So every molecule of HClO4, when you put it in water, is going to dissociate. So you will have the same concentration of hydrogen ions as you do the original molecule. So 4.9 molar is the same for hydrogen ion concentration. We just need to do the calculation, see what the pH is. You know what I'm thinking? I'm thinking we're going to get a negative pH. 4.9. Take the log of it and change the sign. And let's see, we have 2 significant figures. We need 2 decimal places. 0.69 minus 0.69 pH. There it is. That's just to see if you remember that this is simply a mathematical operation, and you can end up with a negative number. As a negative pH. Now, as a practical matter, this value would be more useful for this strong acid. The actual molar concentration would be more useful than the pH. if you had to do any calculations with it. Okay, let's scroll this one up a little bit. There we go. 17. What's the pH of 0.25 molar nitric acid? We're kind of getting into some repetition here. Negative log of 0.25 molar. Why can we do that? Because nitric acid is a strong acid. It completely dissociates. So that's also the concentration of hydrogen ions. Plus, there's only one hydrogen ion per molecule. If we had more than one, then we would have to consider whether to, well, actually, if we had more than one, the second one would probably be weak. So you couldn't use it anyway. That's why for this class, I'm only giving you monoprotic acids for these calculations. So it won't muddy the water. All right, 0.25. Take the log of that and change the sign. And we have two significant figures. We need two decimal places. 0.70. pH is 0.70. 17. 60? Whoa, hold on a second. 0.25, 0.25, 0.25. Take the log of it, change the sign. Oh, my mistake. It is 60. I misread it. All right. 18. A solution has a pH of 3.16. Okay. pOH of this solution is, but this is easy as long as you do it right, not the way I did it earlier. That means that pOH equals 14 minus 3.16. Let's see if I can do that in my head. That'd be 4. 1 minus 8. 3 minus 6. 6.84. Wait a minute. What did I do wrong? Oh. Shoot. 3 from 13 is 10. What am I thinking? 10.84. One of those days. All right, we're gonna have to scroll this one a little bit. Let's see. There we go. 20. Which of the following is true for a buffered solution? Remember what a buffered solution does. In a buffered solution, if you add acid, the pH will only change very slightly. It will not be the same response you would have if you add acid to water. The pH is going to change with the concentration of the hydrogen ions that you deliver. But if you add acid to a buffer, the pH is only going to move slightly. If you add base to that same buffer, the pH will still only change slightly. All right, with that knowledge in hand, A says the solution will not change its pH very much, even if a strong base is added. A is true. About B? The solution resists any change in its hydrogen ion concentration. That's also true. Any hydrogen ions added will react with a conjugate base of a weak acid already in solution. Remember, what you got is a weak acid. Let's use a real example, like acetic acid. Right? So it's going to produce hydrogen ions plus acetate ions. This is a weak acid, which makes this a strong base. Okay. So if you add hydrogen ions to it, they're going to be picked up by that strong base. Just snap them up. So is that true? Any hydrogen ions added will react with the conjugate base of a weak acid? Yes, that's true. And it has to already be in solution. C is true. How about D? The solution will not change its pH very much, even if a concentrated acid is added. That's true. Yep. So all of them are true. So E is the correct answer. Alrighty. 24. A solution has hydroxyl ion concentration of 3 times 10 to the minus 7 molar. The hydrogen ion in this solution, hydrogen ion concentration in this solution is. All right, this is one where you probably ought to go back to the KW definition. So KW equals hydrogen ions times hydroxyl ions. Remember? And this value is 1 times 10 to the minus 14. So if we know hydroxyls at 3 times 10 to the minus 7, then the hydrogen ion concentration would have to be 1 times 10 to the minus 14 divided by 3 times 10 to the minus 7. Okay? We can do this one in our head, right? Just subdivide it. 1/3 is what? 0.333. Well, actually, we only need 2 of them because it's 2 significant figures. And then times, what's this one? This one is 10 to the minus 7 because exponents. This exponent minus this one. So minus 14 minus a minus 7 is minus 7. And then we just resolve it. 3.3 times 10 to the minus 8 molar. There it is right there. So some of these you can do without your calculator. All right, that was 24. Let's see. Let's scroll a little bit. Where is it? There it is. There we go. So we get 2 and 1. 27. A weak acid, HOCl, which is hypochlorous acid, is in solution with dissolved sodium hypochlorite. So we've got sodium hypochlorite in there. What do they have in common? This part of the molecule right here is exactly the same for both of them. If HCl is added, which ion will react with the extra hydrogen ions? So if we add this one, right, and it breaks up into these hydrogen ions, what is it going to react with? Notice what we've done. We've got a situation here where the weak acid is in equilibrium with its conjugate base. We've provided this here. We've provided this here. All right, so they're pre-existing, this one and that one. They're still in equilibrium. Now, if we add extra here, what is it going to react with? Well, it's going to react with this one and move backwards. According to Le Chatelier, it has to go back this way. So the answer is D. There's supposed to be a minus here. I think there's something wrong with the projection. It just doesn't like some of my negative signs. That was 27. And let's see, 28. Which statement is true for a strong base solution with a concentration greater than 1 molar? Okay. Strong base solution. So we're saying that the concentration of hydroxyls is greater than 1 molar. All right. pH, concentration, it's a strong base, concentration greater than 1 molar. pH is greater than pOH. Is that true? What would the pOH be here? Let's see, for A, the pOH would be negative log of 1, right? And what's the log of 1? Well, it's the power of 10 that's equal to 1. And what the base is 10. So that means 10 to the 0 power is equal to 1. So that means the log of 1 is 0. Okay? So pOH is going to be 0. What is pH? pH is 14 minus that 0. So pH would be 14 minus 0 would be 14. So is that true? Yeah. The pH is greater than pOH. Right? 0 is greater than, 14 is greater than 0. So A is true. All right, notice we have 2 of these are true, so we got to look at the others also. pOH is greater than pH. Well, you can't have it both ways, right? It's either one's bigger than the other or the other is bigger than 1. So B can't be true. A and B cannot both be true at the same time. How about pH is less than 14? pH is less than 14. No, pH is exactly 14. So C is wrong also. How about D? pH is less than 0. All right, we can't say that either. pH is much, much greater than 0. So E is false also. That means A is the only possible answer for this question. $28. Wet whistle. All right. 30. A solution with a pH of 2. See, we've got a pH of 2 is how many times more acidic than a solution with pH of 6? We're comparing these 2 solutions, pH 2, pH 6. How many times more acidic, which means what? How many times greater is the hydrogen ion concentration for this one than for that one? Well, we could take the short way and say logarithmic scale means that this one is, we go to 3, 4, 5, 6. So this is 10 times 10, 100, 1,000, 10,000 times. Or we could say, what is the hydrogen ion concentration here? 10 to the minus 2 molar. What is it here? 10 to the minus 6 molar. So what's the ratio of those two? Well, 10 to the minus 2 divided by 10 to the minus 6 is equal to 10 to the 4th, right? Because that's a positive added to a minus 2. 10 to the 4th is 10,000. Either way works. So the answer is 10,000 times here. Let's see, that was just barely peaking, so I better scroll it. No, that's not what I want. There we go. There's another one. Oops. There we go. 32. A buffered solution contains HNO2. HNO2. If it's a buffered solution, what else must it have there? Pre-existing. It needs the conjugate base of this acid. Right? Take away one proton, you get an NO2 minus. All right. So which one of these other compounds will supply that for? Right? Not there. That's NO3. OH, no, Cl. There it is. KNO2. So KNO2 will supply the needed conjugate base to go with this acid. And the key here is pre-existing. It's not a buffer until you have both this one and that one in the proper proportions. We didn't discuss what those proportions are, but if anybody ever asks you the ideal proportions of this to this is 1 to 1, equal amounts. Concentration, equal concentration of this to that, acid to conjugate base. If they're 1 to 1, that's the perfect buffer for that weak acid. Okay? We didn't go into the details why that's true, but that's really not part of this course. I just thought you might need it someday. Okay, 33. Consider the reaction, let's see, acetic acid plus water yields hydronium ion plus acetate ion, okay? This is the complete equation. This is actually what happens. Transfer a proton from here to the water. So you have an acid, a base, conjugate acid, conjugate base. Oh, I just answered the question. Which one is the conjugate acid? Conjugate acid is this one right here. Right there. Okay. Takes care of that. All righty. 35. Which of the following is not a conjugate acid-base pair? All right. We looked at one of these earlier, and the answer was obvious. But what we also need here is to meet the two conditions, right? The what would I call it? The conjugate base of the weak acid has to be the same on both sides. It has to be in the molecule. So if we're going from here, how are we going to get to the conjugate base? Lose one proton. There. All right, well, that satisfies. That's not a conjugate acid-base pair because this is the correct one. That's the wrong one. B, lose one proton. Yep, we get the acetate ion. That's true. C, lose one proton. We get the nitrate ion. That's true. H2NO4 minus, dihydrogen phosphate polyatomic ion. Lose one proton, HPO4 2 minus. That was true. And HBr, lose one proton, and you get Br minus. B, C, D, and E are all true. Conjugate acid-base pairs, A is not. So that's your answer. All right, 37. All right, this one is giving us some actual dissociation constants to go with our weak acids. So given the following K values here, for each one of these, which of the conjugate bases is the strongest? Okay, so this is a conjugate base that we're looking at. Here's a conjugate base. Oops. Let's try that again. There we go. And here. And it's missing its negative sign again. I guess something wrong with the program. Oh, and then all of these. Okay. So where did this one come from? This one came from the weak acid there. This one came from that weak acid. This one came from that weak acid. And this one came from this weak acid. All right. So what do these dissociation constants mean? Well, this one is going to produce, should have put them the other direction. Yeah, well, think of it in terms, we're going this direction. And the K values for this are for this one to that one. And then, of course, you've got the hydrogen ions over here. Okay, so the K values for this one is 5.6 times 10 to the minus 10. This one is 6.2 times 10 to the minus 10. And this one is 2.9 times 10 to the minus 8. And this one is 3.5 times 10 to the minus 4. So let's go back to the question. Which of the conjugate bases is the strongest? Which one of these is the strongest? That is, which one attracts protons more efficiently? Well, the strongest base comes from the weakest acid. So we need to find the weakest acid here. And the weakest acid is the one with the smallest Ka value. 10 to the minus 4, that's the strongest one. So that makes the weakest base. Can't be that one. How about this one? Well, it's a little bit weaker, but still these two are weaker still. So this one can't be it. So it's really a battle between these two. Which one of these is the weakest acid, which would make the strongest base? Now that they're the same powers of 10, we look at the coefficient. Okay. This one is smaller than that one. This is the weakest acid, strongest base. There's your answer. The strongest base is this one. Okay? All right. Gonna get me a drink and fall over here. I'll just scroll it. That. That's good. Number 40. Solid calcium hydroxide is dissolved in water until the pH of the solution is 10.39. Solid calcium hydroxide is dissolved in water, and the pH resulting is 10.39. The hydroxide ion concentration of the solution is what? So, do we have the information we need? Actually, the pH tells you, actually, that's wrong. There. The pH tells you the hydrogen ion concentration. So we can calculate the pOH from this. All we need is 14 minus 10.39. 163. That's pOH. Right? Yep. So now the hydroxyl ion concentration is equal to 10 to the minus 3.61, right? I skipped a couple of steps because we've done them over and over and over again. I just took the anti-log of negative 3.61. So let's see what that is. I get, let's see, 2 decimal places means 2.5 times 10 to the minus 4. Yeah, 10 to the minus 4 molar. There it is right there. The temptation here, I'll admit, was for me, was saying, they're telling us there's calcium hydroxide in here, and each molecule makes 2 hydroxyls. But after it's in solution, it doesn't matter. Doesn't matter how it got there. The pH is this, and the pOH is that, and the hydroxyl ion concentration is that, regardless of where it came from. (41). Okay. Choose the pair of concentrations that cannot be in a given aqueous solution at 25 degrees C. The pair of concentrations that cannot be. Okay, so we're comparing hydrogen ion concentration and hydroxyl ion concentration in aqueous solution at 25. What they're saying is, let's see, the controlling calculation is 10 to the minus 14 equals hydrogen ions plus hydroxyl ions, right? And that's equal to our KW. Okay, so if we look at our choices, A choice is, let's do it this way. Hydrogen ions, hydroxyl ions here. There we go. So for the first one, they're saying 10 to the minus 13 here. and 1 here. Is that possible? Well, it would have to be 1 times 10 to the minus 13, which would be 10 to the minus 13. That's wrong. Can't be. How about this one? 10 molar and 10 to the minus 15. This one times this one will be 10 to the minus 14. That's true. 10 to the minus 3 and 10 to the minus 11. Minus 3, minus 11, minus 14. That's true. And then the last one, 10 to the minus 7 and 10 to the minus 7, 10 to the minus 14. That's true. But all of these can exist. No, we've got one bad one up here. So A is the only one that cannot be. Right here. Now, if that value were 10 to the minus 1, they would all be valid. But it isn't. So A is the answer because it's the wrong one. Let's see here. 42. What is the pH of a solution prepared by dissolving 96.1 grams of sodium hydroxide? 96.1 grams of sodium hydroxide in enough water to make 3.2 liter solution. The volume is 3.2 liters. All right. And he wants to know the pH. What are we going to do? We're going to have to calculate the hydroxyl ion concentration first because that's what we have. This many grams in water completely dissociates. But we don't know the number of moles yet. We need to know the number of moles. So what's the molar mass of sodium hydroxide? Well, let's see. Sodium is 23. Oxygen is 16. And hydrogen is 1.01. That's so 40. 40.01. Right? Divide 40.01 into 96.1. Let's see, I get 2.402. Actually, I hung on to an extra decimal. Officially, I should only keep 3. So this is the number of moles of what? It's moles of sodium hydroxide, but it's also moles of hydroxide ion because this is a strong base, completely dissociates. So this is also hydroxide. Now we can calculate the OH concentration. 2.402 divided by 3.2 moles per liter. I get 0.751. 0.751 molar POH equals negative log of 0.751, which is, let's see, log, 0.125. 0.125. That's the POH. So the pH is equal to 14 minus 0.125. Let's see, 13.8 13.8 0.875. All right, round it off. Here we have another possible argument. We had 3 significant figures that we carried through the calculations, so we should have 3 decimal points in our pH. But this would be the best answer, but you could argue none of these because it's not 0.875. All righty then, 42.